When you ask a question and then you figure out the answer, you learn a lot more than if someone just tells you the answer. So do you ask a lot of questions? Did you really annoy your teachers? But asking questions isn't enough. You don't really learn until you figure out the answer to the question. And this is where you need a teacher. The teacher is there to guide you to figure out the answer on your own, but without simply telling you the answer. But it's a really hard thing for the teacher to do. So a lot of teachers end up just telling students the answer. I'm Keith Sawyer, and this is The Science of Learning. I'm here with Professor Joe Krajcik, and he's an expert in helping teachers help students learn and without giving them the answer. Joe, this is the million-dollar question in the learning sciences. How can you learn something without the teacher telling you the answer?
That is a million-dollar question. And we all have background and experiences, our prior knowledge that we need to build on. And so the critical aspect that a teacher has to do is figure out where you are, and then you have to build on that, not by telling the student, by giving them other experiences which will allow them to connect their ideas together and go a step further. And so what often happens is that the gulf or the distance, you might say, between what a kid knows and what they're trying to figure out is too big. So they can't necessarily make those connections. The goal should be for the teacher or your partner, your cognitive partner, the person you're working with, let's think of the teacher as your cognitive partner, to realize where you're at and provide that scaffolding, that support that can get you a little bit farther. And that's how you can systematically build your knowledge up over time. And that's a much more valuable way of thinking about building knowledge, because if you build knowledge in that framework, that knowledge is going to stay with you as a learner, and you're going to be able to use that knowledge when you experience something new that you want to figure out, and you can build on it. And so often what happens is, as learners, we don't have this knowledge that is connected, and so we can't really build on it. And often what happens is we're given information in class or in our learning environment that's too far apart, and we can't make those connections. So knowing where the learner's at and providing supports that can just move them a little bit forward is beneficial. I always like to tell, it's an old analogy, but I think it's a meaningful analogy that a lot of people can relate to. If we just give a kid and put him on a bike and tell him to go, he's going to fall over. And so we put training wheels on the bike, and the kid can then use the training wheel to move forward. And then, of course, the parent often takes the training wheels off. We don't keep them on. Otherwise, I can't use my bicycle independently without the training wheel. Often the parent takes the training wheels off and then runs along with the kid to help guide him first till he gets balanced. Now, we always fall a little bit, but that's productive struggle. Just like when we're trying to figure something out intellectually, we're going to stumble a little bit, but then we get back up and we keep trying to make those connections and move forward.
That's actually the motto, the tagline of this podcast, is that learning is creating something in your mind. But that sounded pretty abstract. So can you give an example of what you mean by that, of building something, building knowledge on top of what you already know?
Well, force is a very complex concept for kids. And often young learners, typically think that you have to keep applying a force in order to allow something to keep moving. Well, it's actually the opposite, right? So if you want to basically change the movement of something, either the speed or the direction, then you have to apply a force. But that's counterintuitive to most people, because in our life, we live in a frictional world. And because we live in a frictional world, we always have, and that friction actually resists the direction and motion in which we're trying to move. That friction will always slow us down. So a lot of people typically think that I have to constantly apply a force in order to keep something going. So one way to support a learner is to try to make experiences related to kids in which there isn't friction working against your motion. Now, on Earth, that's pretty hard to do, but we have design systems that can do that. You can talk about ice, of course, if you go skating, but not all kids go skating. But that would be one appropriate manner to say, well, if you take a ball and you give it a push on a surface that's all just smooth ice, well, let's stop, and so that it will it keeps going. On the other, and then you could say, okay, now so we could do it on ice. Let's now do it on a smooth surface, and you would see that with that same exact push, the ball doesn't go as far as it does on the icy surface, and you could go into an ice rink, for instance. Then you could go from ice rink to a smooth surface to a slightly rougher surface. Give the ball the same push, and you'll see that it'll stop sooner. And you can then go to a really rough surface. And so kids will realize then that, if I give a push to something on a smooth surface, it keeps going. If I give a push to something on a slightly less smooth surface, it will stop sooner. And if it's rougher, it will stop even sooner, etc. So they realize that it's not a force that's needed to keep something going. A force actually will stop something. And of course, a clear indication of that is I could push the ball and I could not have my hand there, right? I could push the ball, my hand's not there, and the ball just keeps going. But if I put my hand there, the ball automatically stops because I applied an opposite force on it, basically the ball hitting my hand. So you can take some challenging concepts like understanding force and give kids some other experiences on which to tag along with. Now, hopefully, some of those experiences are things that they experienced in their daily life, like if they've ever gone ice skating or gone to an ice rink, etc. You could also think about rollerblades, if kids rollerblade or skateboard, right? So skateboard's the reason why you don't have to put much. Obviously, when we push it, it goes much farther than if I had really nice wheels on my skateboard. It goes a lot farther than if I had wheels that were all kind of squeaky and stuff. So you can provide kids with experiences that they could build on to help them understand that a force get something started or to change directions or change speed and not to keep it moving.
Right. I'm thinking you're talking a lot about experiences or having, seeing something happening in the world, or like you said, in the real world, you don't see force equals, what is it? Motion times acceleration. And then you learn this in class and you memorize the formula, and then you pretty much forget it right away as soon as the course ends. Is that right?
Right. Often in school, so force equals mass times acceleration. I'm not sure what you said, but
right. I didn't see. I forgot it already.
I thought I would just modify it quickly. Anyways, often what happens if we have these experience, we're given definitions or equations in schools, and we really don't try to tie those towards experiences. And so if we really want to support kids in building deep knowledge, we really need to give them experiences which to build off of. And often those fundamental, and that's why it's so critical at early ages. And as you go on in life, they have really key experiences on which to tie things to. Now, after we build up, at least in Joe's theory of the world, once we actually build up knowledge and we've made connections, then it's easier to take something abstract and tie it into. But often experiencing something, either virtually or firsthand, is really critical for building knowledge. I know when I was, and I still do nowadays, my background's in chemistry, even though I gave a physics example. But in chemistry, I would always, in my own personal learning as a teacher, I would always have kids build 3D models to understand the rotation of molecules. So it's really hard for many people to conceptualize the structure of various molecules and how they interact with each other and fit together. But if you build a model, and you can actually see those, how they can, what they look like and how they, what happens when they rotate, that's much better than looking at, just telling kids about various structures. So I really believe in firsthand experiences are just critical for developing deeper understanding, because when you have those firsthand experiences, you can really make much better connections.
Right. So, what do you mean by building a model? I guess so. I don't know, a model sounds pretty abstract. So, I can remember putting together these balls and sticks between them to make a molecule. So, that's what you mean by a model, right?
Well, that's one type of model. But like for me, you want the molecule to be able to explain something or make some prediction. And of course, often in instruction, that's left off. We usually, like you just said, you put six things together, and you're basically just getting the description of the thing in 3D rather than in 2D, or right. So I like to always push models towards explaining. But even a simple model, which you're trying to provide an explanation. So, for instance, if I was trying to show kids that there's lack of rotation around a double bond, right? You can actually show that with a physical model, because the physical model doesn't, when it has two bonds or two sticks, doesn't allow rotation, right? So it's partially it helps kids with an explanation that they don't rotate. And so you want to make sure that whenever you talk about a model, although models are abstract, and in the case what we've been just talking about, we're talking about a 3D model, or like a real physical model. Those aren't as, because you build them, they're not as abstract as a paper and pencil model. But all models are somewhat abstract. They're not necessarily, they're not illustrations of reality, but what they should do is explain and give you potential to predict what's happening or what will happen.
Wow, that's starting to sound kind of, I don't know, I was going to say trippy. All models are abstract and they allow you to explain and project. I mean, I know what you're talking about because I'm a learning scientist, but it sounds like a really powerful thing, something that you can abstract away from reality and use it to explain. I mean, that's just a really powerful concept. Is that hard to get across to students, just the basic idea?
I think modeling is a very challenging concept. And one of the things I like about some of the changes that have occurred in science education over the last 15 years or so is actually a real emphasis on having kids design models. I don't know about you, but when I went through schools, I was always given models, right, with someone else's model. And I wasn't involved in the development. But of course, I could use that model to make a prediction, but I was not allowed, I did not develop them. But what's really been fascinating, at least for me as someone who's really interested in promoting science education, has this real emphasis on kids building models. And when kids build models, they are abstract. But if I build it and I can show how it actually can account for something, that's a really powerful idea. And if we can start doing that at really young ages, then that develops with you. So often these very challenging concepts, like understanding models, that they are tools to predict with, although they're not actually representations of the world, they're actually abstractions of the world. But if I can build them, I can actually use them to explain and to predict future events. That's a very powerful idea. And if we can start at early grades and do that from elementary through middle through high school, you really end up with a learner developing that kind of understanding. So when you said to me, Is that a tough concept to understand? The answer is absolutely yes. And one of the things in education that we have to understand is this notion of ideas developing across time. If I do that with a third grader, have a third grader draw a model, for instance, of why they think something will stop or keep moving, will all those ideas sink into the kid? No, but it's a start, right? And you want to, it's a start. And relating back to what I talked about at the beginning about a scaffold, we want these experiences that kids have to develop across time. And often, and I guess this is another exciting thing for me in science education across the last 15 or so years, we've taken a much more developmental perspective on students developing these really challenging ideas. So rather than just giving them to them in a straightforward, paragraph, we now develop some of these ideas over a much longer period of time, realizing how challenging these ideas are. So when I was in school and you were in school, we basically memorized Dalton's atomic theory, right? And the kids don't, at least in the work I do, we don't do that. Basically, kids slowly develop ideas of how the physical world is built up.
Right. And just to clarify or to make sure I got this right. So when you say building models, the students, they're not just looking at a picture of the correct model and making a copy of it because that would be the teacher telling them the model. The students are trying to figure out what the model is, right? Aren't they? Don't they have to kind of explore and engage in inquiry? They have to construct the model in some way, right?
Absolutely. So when I said kids build a model, they're not copying. Uh,
Yeah.
the copying isn't going to lead to the kind of connections where students are going to be able to use their knowledge in future situations. It's actually them trying to put ideas together, right? They may have had experiences and they could ask then, how might this work? And trying to build this model. So for instance, just to switch topics from it, let's go to an environmental topic that might be more understandable to more teachers out there. We could go to water quality, for instance, and students could be collecting data on the water quality of a local stream. So they might basically come up with ideas that, okay, if things are really hot, if the water level is really hot, that's dangerous for life. If the pH is not with around between 5 and 8, that could also be dangerous for life. They could collect dissolved oxygen is to realize that streams have to have dissolved oxygen in it. And of course, then they need to build a model to be able to explain what would happen if I have these various factors. And now we're only looking at 3 factors: dissolved oxygen, temperature, and pH. If I make the pH really low, what happens to life? And then one of the things they could do is they could actually collect some data, not by using an animal, but they could use some vegetation. And they could see that if I have water levels that have a pH lower than 4, that the vegetation isn't going to live in it. Of course, then it's an abstraction to more animal life. But of course, we don't want to harm any animal, even if it's a tiny little creature. So we don't experiment with animals. But we can notice that when you have like a Elegia or some other water plant in the water, that below 4, it becomes yellow and basically dies. And so we would see that if we could make a model that would say that if my pH is, starting to approach 4.5 lower, that the water quality is very poor and therefore does not sustain life. We could do exactly, and that's a critical factor. We could do the same thing with temperature. We could see that, at a certain temperature point, life is not sustainable any further because we see the organism, or in this case, the plant material, starting to die, and that we can realize then that between these ranges of certain temperatures and certain pHs, they actually support life. And so we want kids to put that together. Of course, I could write a nice, clear paragraph about that, but if I write a real clear paragraph about that, that's not going to help the kid. What's going to really help the kid is by actually doing some investigations, as you said, some inquiries, some explorations, and figuring out that when the pH is below 4.5, it results in does not sustain the life of a plant in the water. Same thing could be true with dissolved oxygen and with temperature. Now, I said I want to clarify one thing. That doesn't mean that I don't want kids to read. Reading, you obviously read, I obviously read, I love to read, and I want kids to love to read as well. But it's where we give it to them in their instructional standpoint, in their instruction sequence, that I think is really critical. And often what happens if we front load all the facts to kids, and either through lecturing or through reading, and that doesn't give kids a chance to figure things out on themselves. And for me, it's when you get involved, and it's not just for me, I think the research is pretty clear that when we get kids involved in figuring things out, that's what supports their not only their learning, but also their engagement. They're really their desire to want to learn. And so we have to put them in situations in which they become curious, in which they want to try to figure things out, put ideas together, so they actually build their knowledge. And somewhere along the line, we want to make sure we have that can read. We want to certainly give them readings. We certainly want them to write as well. So it's not just manipulation. In fact, if we just do manipulation, like you said before, a person just copying with an image, that's not figuring out, that's just copying. So we want to put people in situations which they are really interested in making sense of something and putting the ideas together.
Right. How do you do that? How do you foster that curiosity in children? Because I think it really takes that to motivate them. This kind of learning seems to require a lot of sustained attention and motivation.
Yeah, personally, I think it's really important for having whatever age level you're talking about. If you're talking about third graders, if you're talking about seventh graders, if you're talking about high school students. I don't really do a lot of work in college, or adult learners, but so let's just stick with the realm I know. But I think I would predict the same thing is true with adult learners as well. You have to put them in situations in which they're going to actually find meaningful. Not all situations are going to be meaningful for kids, right? So you're going to be someone interested in some ideas more so than I am. But if we can actually get kids to experience it, then we get a common experience among the class, and that's going to help, right? So I always like to start off with having students in my class have an experience, a firsthand experience wherever possible. So I'll give you an example from one of the projects I worked with, which is called Multiple Literacies and Project-Based Learning. This was actually in elementary materials. And one of the units that we created was a third grade unit that focused on adaptation. And we actually we encourage teachers to do this in the fall of the year, particularly if you live in North America, because squirrels are very active in North America at that time of year. So we actually take kids out and have them observe squirrels and the behaviors of squirrels to see what they're doing, right? So they can notice that the squirrels are actively looking for food. They're building stuff, and then we introduced the driving question of the unit. And the driving question of the unit is supposed to be something that can propel and sustain the learning for students across time. And of course, the driving question for this unit is, how come I see so many squirrels, but I don't see any Stegosauruses? And as a third grader, they kind of love that question. And so we take them outside again, and based upon what they observe, we ask them to ask questions, like what kind of food, and the kids will come up with all sorts of questions related to like what kind of food do they eat? Are they playing with their friends, or are they playing with the other squirrels, or are they chasing the other squirrels because they're mad at the other squirrels? Um, so they come up with a series of questions, and then through the unit, we actually get to, and the experiences the kids have, they actually get to respond to those questions, and they realize that squirrels have been very adaptive to their environment that actually has led through their survival for many years. And of course, they have experiences to realize that squirrels have, as I mentioned, really adapted to their environment. I don't know if you've ever noticed, but a squirrel can actually move down a tree head first.
Yeah.
Just imagine you trying to do that. I know exactly what would happen to me at any age, right? I'd fall straight on my head. Even when I tried to climb straight up the tree, I would fall. Yeah, but squirrels have developed these very powerful back legs that really has been an adaptation to their environment to allow them to survive, both to gathering food and to survive from predators. And so the unit, based upon these experiences that kids have about observing squirrels, we also show some really fun videos of squirrels. I mean, they'll go through anything to get to some nuts, and so it's really fun to watch them try to work their ways through some mazes. So we show these engaging videos that can, and having kids go outside and observe the squirrels and have them ask questions that will actually motivate them and keep them engaged to try to figure out, to learn a challenging idea for a young third grader, which is that organisms basically have adapted to their environment, and the ones that don't die out, and the ones that can continue to live.
Yeah. And I know where I live, it's a very forested area, and there are squirrels everywhere. And like you say, certain times of year. So project-based learning, and you're very well known for this type of pedagogy, which I started the episode talking about asking questions, and you referred to a driving question. It's very hard to ask a good question, and by that I mean to ask a question which will lead to a good learning experience. So rather than ask students to come up with their own question, it's you have these well-designed pedagogical units where you have selected the question ahead of time, and it's called a driving question. And then there's a pedagogy where you guide the students through a process of inquiry and building models and all the other things we've been talking about. Can you give an example of a success story, a particular school or a classroom or a project where you think it's exemplary, where you would tell any other school in the country that wanted to do this, where would you tell them to go? Like a case study of it worked out so well.
Well, I just talked about the third grade multiple literacies and project-based learning, one of their units, which is how come I can see so many squirrels and not any Stegosauruses. That was that was a very successful project, actually, and you can say why. Well, one of the reasons why is because we not only have wonderful testimonies from teachers, we actually wrote a case book related to this, but we also did a very carefully designed study on our own to see if third graders would actually learn more in these kind of environments than students who had science instruction in third grade as normal. And we showed a very substantial increase in students' learning, as well as their interest in science. But beyond that, there's also the testimonies of the teachers and them saying that how it made science, because as you well know, a number of elementary teachers don't like to teach science because of their bad experiences they might have had or their lack of interest in science. But because of the question naturing of our units and the way we carefully support students and developing understanding across time, they find the units very motivating as well. So the multiple literacies and project-based learning curricula, I think, is a very strong example for in elementary classrooms where we show we both have teachers saying very positively about their unique experiences in using it, but also really good learning data on students. Similarly, I did a project with my good colleague Barbara Snyder, and this is changing grade levels 100%. We went from third grade now to high school chemistry and physics, and we designed some materials, not a full year. The interesting thing about multiple literacies and project-based learning was a full year curriculum. The crafting, engaging science environment, which I did with Barbara Snyder, we just had 3 units. 3 units in chemistry and 3 units in physics. And in those, which were challenging high school units. So I think you've studied the periodic table probably in high school, maybe in college. A lot of people have, at least had experience in high school. And, they could never figure out why they're memorizing all those numbers and all those letters. Of course, as I said before, I'm a chemist. I never understood why I was memorizing all that stuff either. It's not actually a fun way to learn. So we sort of changed it around as an example. We changed it around. One of our units was on the periodic table. But we started the unit out with the question, how come I can eat sodium chloride, table salt, but I can't put a piece of sodium in my mouth? And we also at the same time have kids experience what happens when you take a little tiny piece of sodium and you drop it in water. You may know that you get a massive explosion. So the kids see that you get this explosion. If you put a big, you have to be careful. You put a big piece of sodium in water, you will get a massive explosion. And of course, in classrooms, we don't want that to happen. So we just put a small pea-size piece into a 250 milliliter graduated beaker filled with water. We put a pea-sized stone in it, and of course you get a nice little flare up, and the thing moves around really quickly, and you can't possibly put that on your mouth, because you saw a little flame, it would burn your mouth. So the question becomes, well, how come I can eat sodium chloride, but sodium, which sodium chloride's made up of, is so very reactive? So that's the driving question and the driving experience that leads off that unit for students to study some fairly challenging ideas. But we can always then link it back to the sodium, right? It's a real world experience that they have. We do the same thing with chlorine. Chlorine is a very reactive molecule as well, that we certainly don't want to be around. And so we actually show, we do some experiments with the kids, with the students, and the students to really show how reactive chlorine is. And so this provides the motivation and the drive to learn about the structure of atoms and why atoms actually come together to form new things, which basically, in this case, sodium chloride is not harmful, but is really important. Many of us like to put it on our food to make it taste a little bit better. And that was a very successful project as well. We actually did, once again, a very systematically controlled study with students both in the state of Michigan, but also in Southern California, both in LA and Sweetwater, which is right on the border between California and Mexico. And we compared how kids did in the crafting, engaging science environment units with traditional high school chemistry and physics. And of course, both the state of California and the state of Michigan used the same standards, which were the next generation science standards. So we could feel fairly comfortable that everybody had this, was moving towards that instruction. And yet the kids in the crafting, engaging science environment substantially outperformed the kids in the controlled environment.
Oh, and that name is Crafting and Engaging Science?
Crafting, engaging science environments.
Oh, crafting. So that seems to echo building again.
Yes.
Right, right. And it sounds like another situation where you could do the modeling.
There's a lot of modeling that's done in the crafting, engaging science environment work. Both in it's one of my key instructional strategies that I love to use, partially because it's a multimodal experience. Kids have to actually take their ideas and actually make either make a three-dimensional model or a two-dimensional model, either on paper and pencil or sometimes on the computer. And that act of actually creating and putting their thoughts into that and then showing that it works, really leads towards understanding that can really last over a long period of time. And so modeling is a really essential aspect of the work I do. And of course, one of the things we do when we do build models, we stress the importance. Does your model actually, can it explain the phenomena you're talking about? And is it consistent with all the data you have? And so we always ask those questions as part of the modeling experience. But in addition to modeling, I also do a lot of work with kids, making sure kids can make claims, support their claims with evidence and scientific reasoning. Once again, it's a very important practice in science. And often what happens also in schools are kids are given claims already that have been made, and they don't get to make the claims themselves. And so we actually want kids to experience, engage in investigations or inquiry, as you mentioned, and make their own claims and say, do I have appropriate and sufficient evidence to support that claim? And make sure they use scientific reasoning to justify it. And of course, that is also a wonderful instructional technique. So the two techniques that I make use of a lot in developing learning environments and creating learning environments are actually having kids construct models and or design these claim evidence and reasoning statements.
Right, right. And
We also, as I tried to insinuate before, I mentioned that after kids experience a phenomena firsthand, we like to get them always to write their own questions. And as you said, asking good questions is really hard. And so we try to, once again, if we can systematically support kids in asking good questions from elementary through middle through high school, I think kids are going to get better at it. Everybody's going to get better at asking questions. It's almost a lost art. We don't let kids ask questions anymore. And so we really focus these different grade levels on kids asking questions. And as they get to high school, the very importance of making sure kids ask questions that can say how it might impact something else. Asking more questions that could put together various ideas and variables.
so, how do you do that? How do you help students ask good questions?
Well, I think the first thing that, as I mentioned it already, is you got to get them to experience the world, right? You can often in science classroom, it's been void of experience, and of course with the cost of equipment and also some legal issues, we don't see kids actually experiencing science as much as perhaps as I did when I was a kid. So I really try to get students to experience phenomena firsthand. And when they experience firsthand phenomena, it can raise a question. And why this might sound very trite, allowing kids to ask a question is the first step in helping them learn how to ask a question. If we don't give them permission to ask and accept their question, then they're never going to feel comfortable asking questions. So I think it's really critical to get kids to have experiences and then ask questions. And of course, then we can work with them to refine those questions, to get them to realize that, okay, the kind of questions, there's different kind of questions. And the various different kind of questions can be really valuable. So you can have a descriptive question. So I can support kids in asking descriptive questions to get them to really understand what the situation is like. I can get them to ask more causal questions where they actually relate how one variable will actually impact one variable. But if I don't start off with them experiencing phenomena, then say, oh, now we're going to work at writing questions that explain how one variable impacts another variable, it doesn't mean anything because they don't have the experiences to link one to the other.
Right. I think that's a great way to end our interview, is to celebrate the question askers. I know from creativity research, my own area is we talk about problem finding and question formulation and question asking as being one of the most important aspects of exceptional creativity. And now here we're finding that in learning as well. So this has been The Science of Learning. If you've enjoyed this conversation, I hope you'll like the episode and subscribe to this podcast. And Professor Joe Krajcik, thank you so much for joining me today.
Oh, you're welcome, Keith. And thank you. If anybody has questions based on this podcast, please feel comfortable emailing me at krajcik@msu.edu, and I'll be glad to respond to your questions.
Professor Joe Krajcik is a leader in the learning sciences and in project-based learning. It really is an honor to have him on The Science of Learning. If you like this episode, I hope you'll subscribe to the podcast.